question and look at what is a sampled structure versus a differential equation structure. And a lot of times differential equations are the starting point for what we want to build. Now we can think about this in a frequency domain. We can think about this in a time domain. Certainly if we're going to make that transformation, we need to look at the difference to kind of therefore approximate the continuous time derivatives. That definitely in the first and second order case, which gives me something that does fit in the frequencies domain. The interesting part is when I then look at the difference equation, where I'd have an a squared here, a over q, and so forth, what I notice is I get a nice h of z of this form. Okay, great. And I can talk about where its center frequency, and I can think the center frequency is because what it actually is in a real frequency space, because I can then take a look at its frequency response and build that. But one more interesting question here is asking the question of, well, can I start solving this in terms of its time response? So let me look at a set of parameters. One where a is equal to 1, so that means that my sampling time is the same as my time constant. I'm going to pick q equal to 1, so it means that I've got in the continuous time domain, I know I'm going to have two roots, but they'll be complex, and they'll be complex conjugates of each other. And that would mean I would expect a q equal to 1 in a continuous form to have something that would sort of, as a impulse response, would sort of go up and then sort of eventually come back, oscillate just a little bit around 0 in steady state. That'd be great. Well, what do I see? Well, let's jump to the conclusion. This is actually the solution you'd want. This is actually the other solution that's possible, but you may not want to, this doesn't actually quite fit. So not quite what you're looking at, but this would be the solution you want, where it start off 0, come for the impulse response, comes up, you have a little bit of a peak in between if you're actually doing continuous, and then it comes back down, comes underneath, and then comes back to the solution. There might be a little bit of bouncing around in here, but very, very small amount. And this is actually what you would calculate. This is exactly what you would expect from the step response for this kind of a system. Okay, very cool. The question is, how would you actually solve for that particular response? Well, you'd start off by going, well, I know what my h of z is. If I calculate for there, I can then plug in values. So pull the terms together. And I'm going to do some things here because I'm going to be looking at a particular form. What form am I looking at? Well, if you look at the bottom, there is an interesting term of a transformation of a sinusoidal signal that is maybe increasing or decreasing, and what its z transform is. So I'm going to get something in the denominator plus, I'm going to look at what its term and its first delay term is. Well, interestingly enough, when I go through all of this, I'm going to get no delay terms. I'm going to be thinking about that. But before I do that, I want to look at the denominator term and realize I need it to be 1 minus 2 over 2 times a times cosine of something, and then 1, and basically an a squared z to the minus 2. Well, it turns out for this particular problem, because I'm going to have 3 pulled out here and a 1/3, it's like, wait, that gets a square root of 1 over square root of 3. I can work through, say, 2 over square root of 3 and 3 over square root of 2. It's like, wait a minute, that gives me my a term, that gives me a square root of 3 over 2. Wait, that's a cosine. I know how to kind of frame that in this structure here. It gives me a way to think about all of those things. So now the question is, once I have that, then I want to figure out what's going on in the numerator term. I could either look at a minus pi over 3 or 2 pi over 3. Why? Because once I figured out these two terms, omega 1 hat and a 1 hat, what I'm now left with is realizing, I need to figure out, well, is 1/3, if it's a pi over 3, that gives me a 2/3 here, which is exactly going to fit with what I pick for omega 1. That gives me this block, that gives me this solution. I could have picked the reverse, which I could have picked theta as a sort of a 2 pi over 3, not a minus 2 pi over 3. and that would give me a plus here. That would be great, but that would have actually given me this structure. And the only way I would have gotten this solution in this piece is by having an extra minus term, which would have still flipped it. So what's really cool is that I actually get this nice solution and I can analytically solve it directly.